So this video covers the parasympathetic nervous system, which you can see here summarized in contrast with the sympathetic nervous system in all of the different ways that it has opposing effects. One interesting one you can see at the top is the effects on pupils. In your eyes, your pupils dilate in response to light and constrict in response to darkness, but the sympathetic and the parasympathetic system have influences over this pupil dilation and constriction. So if you keep light constant, you can see the emotional system play out in people's eyes. Now, if you're a weightlifter, you might already have seen this in action. If you look at your eyes in the gym mirror while you lift something heavy, you might be able to see your pupils dilate. And this is because the sympathetic system must mobilize whenever you lift a heavy weight. So start to observe the people around you. The biggest influence on pupil size, as I mentioned, is how much light there is, but given equal amounts of light, the amount of arousal someone is experiencing will influence their pupil size. When they are really sleepy, they will show slow oscillations in pupil size. You might have even heard the notion that if someone is very attracted to someone else, they will show larger pupils. Is this really true? At least when actually thinking about sex. So for instance, this has been shown by asking people to come into the lab, fill out a sexual orientation scale, and then watch videos of men and women masturbating. The more strongly someone identified as being attracted to the opposite sex, the bigger the difference was between their pupil size when watching someone of the opposite sex versus the same sex. So these graphs on the y-axis, they subtracted pupil size when watching someone of the same sex versus the other sex. And you can see for women, the more that they identified as heterosexual, the bigger that difference was, and for men as well. So next, take a look at this diagram. Take a look at the different ways the parasympathetic and sympathetic systems are organized. So this here is all one nerve, whereas on the other side in the sympathetic system, you can see that there are many different branches. This one nerve is called the vagus nerve. And it makes things quite speedy, actually, for this parasympathetic system, whereas in the sympathetic system, communication must travel through ganglia in the spinal cord, which actually slows it down a little. It might seem strange at first that the parasympathetic system is the one with the more direct connection with many internal organs, including critical ones, in a crisis such as the heart. Why would we want the vagus nerve, which is connected to the system that's involved in relaxation, to have a more direct connection to the heart? In a crisis, wouldn't you want this sympathetic system to activate the heart more quickly? Well, it's really interesting. The system is set up in a surprising way, and we'll take a look at the heart as an example of this surprising way that your nervous system is set up. So here is a diagram of the heart, and the rhythm of the heart is normally determined by a pacemaker site called the sinoatrial node, located in the posterior wall of the right atrium. So this stands for right atrium, and this is the sinoatrial node. And this node consists of specialized cells that undergo spontaneous generation of action potentials at a rate of 100 to 110 action potentials, or beats, per minute. This intrinsic rhythm is strongly influenced by autonomic nerves, with the vagus nerve being dominant over sympathetic influences at rest. So if you think about it, your resting heart rate is probably quite a bit lower than 100 to 110, which is this intrinsic rate of the heart. So what's happening is that the vagus nerve is bringing the resting heart rate down to 60 to 80 beats per minute. So I want to show you something. This is a demonstration of how the heart contains its own pacemaker cells. So I'm going to show you a video. It's a video of a heart outside of its body, It's not being stimulated in any way. It's just receiving tubes to bring it blood. So if you're grossed out by internal organs, you might want to close your eyes and not look, but otherwise it is really cool. So here is this heart. It is, as I said, someone, they took it out of someone's body, and I'm going to play this video, and I want you to try to count the number of times this heart beats. I'll say 3, 2, 1, start, and then I'll say stop about 12 seconds later. So please try to count the number of heartbeats that you see. 3, 2, 1, go. How many? Okay, so that was how many heartbeats did you count? I don't know about you, but I counted 20 beats over that 12 seconds. And there are 5 12-second segments in a minute, so that means this heart is beating around 20 by 5 beats or 100 beats per minute. And this is amazing. This here is a heart that is detached from its body, and it just keeps on beating at its intrinsic rate, set by its pacemaker cells at around 100 beats per minute. So this is really interesting because the heart normally at rest beats around 60 beats a minute, but what we're seeing is that intrinsically, if we detach it from the vagus nerve, detach it from the influences coming from the brain, it would start beating at around 100 beats a minute. So this is a very interesting way for the body to have been set up. It is as though the brain is a brake that is constantly on the heart and other organs as well, that is slowing them down and relaxing them. And that very speedy connection to the parasympathetic system, what it allows is for the brake to be removed. So your heart is always ready to go. Its intrinsic rhythm is fast, and it wants to beat at around 100 beats a minute. But most of the time when you're at rest, there's a brake on that from your parasympathetic system that can be removed really quickly. Your system doesn't have to gear up at all. It just instantly is set back to around 100 beats a minute, and you can start getting fuel. That blood can be sent rapidly to whatever parts of the body need it. So the vagus nerve is interesting in many ways. It is the primary influence from the parasympathetic system because it connects to so many organs. You can see it wanders throughout the gut, goes to the stomach, goes to the lungs, the heart. And it not only sends information to these regions, but it also receives a whole lot of information from these regions. So it has a bi-directional communication pathway between the brain and the body. So let's give an example of how this bi-directional pathway works. You get home, you're tired, you're stressed, you down a pizza, you collapse on the couch. Then what happens? Your stomach sends signals to your brain through the sensory nerve axons in your vagus nerve. Your brain sees that your stomach is churning away, which is a usual parasympathetic action. So it sends signals back down through the vagus nerve, triggering other parasympathetic responses, like slowing down your heart rate, putting some glucose back into storage, and reducing all that norepinephrine that your sympathetic system was pumping out all day. Remember that norepinephrine signature of the sympathetic system that you learned about in the last video. So you start feeling more relaxed, which is why, for some people, eating is a way of reducing stress and anxiety. In fact, it can feel so good that even though you might feel full, you continue eating. The rate of action potentials traveling through each division is known as your sympathetic tone and parasympathetic tone. The autonomic system is designed to have the parasympathetic system be the one that is dominant most of the time, keeping the caged animal that is your sympathetic system in check. Then this here is a diagram of what your system looks like when you are in a high parasympathetic state. And here it's being argued that this would be induced by meditation, but it could be any time that you're relaxed. And what you see is that you have normal salivation, your blood pressure's down, you're breathing slowly, your heart rate variability is high. We'll be talking about this, as I mentioned, we'll be talking about this later. Your heart rate itself is low. Your skin conductivity, basically the sweat that you're putting out, is low. And your digestion is going really well and moving along. So all this happens while you're relaxed and the parasympathetic system is dominating. If you have the sympathetic system dominating for long periods of time, what you will get is a dry mouth, not much saliva, high blood pressure, you're breathing fast, your heart rate variability goes down, your heart rate goes up, you're sweating more on your skin, and then you also aren't doing much digestion. So it can be easy to think about these two divisions of the autonomic nervous system as opposites or even rivals, but that's not quite right. It's a little more accurate to think of them as two ends of the scale. Sometimes you find yourself in balance somewhere in between. Sometimes one system is more active than the other. Another way to think about these systems is that they are both essential for optimal function, but they serve different purposes. We have been mostly talking about the negative side effects of sympathetic activity, but I want you to keep in mind it's also the system that is most important for new learning in the brain, for making new memories long-lasting by building new synapses. But this activity creates waste, including the amyloid beta that is the building block of the plaque that builds up in older adults' brains and is the hallmark of Alzheimer's disease. As we mentioned already, you need to be able to clear out that waste, and you also need to stimulate the new growth that leads to new pathways in your brain. So the way that this system does this is that it has intermittent times during the day, during your 24-hour cycle, that the sympathetic system is really active when you're awake and alert, and then there are times when the parasympathetic system is really active when you are asleep, especially during deep sleep. And recently, researchers have discovered that the parasympathetic system is essential for clearing out the waste that high levels of brain activity create during wake, and that it's during deep sleep that we get enough parasympathetic and low enough sympathetic activity to achieve this optimal waste clearance. We'll talk more about this exciting new research in our module on sleep that's coming up.